Okay, Anna asked me if I would look at this problem in class. And sure, because this is a great example of just following through the steps like we had in lab on Tuesday.
I appreciate how you say that.
Well, it is. It's a great example, right? Because seeing the steps and doing them, it's a lot easier to see them than to do them. So we have a yo-yo that's constructed by attaching 3 uniform solid discs, and it's going to rotate about the axis that is shared by them. So the first thing I'm going to do is just look at the moment of inertia. This is 3 cylinders. What's the moment of inertia for a cylinder rotating about its symmetry axis? You look it up in that little table, little big table. I showed it to you in class. In lab, I guess it was. Right. And so you find that if you have a cylinder that is rotating about its symmetry axis, it's 1/2 mass times radius squared. Now remember, the moment of inertia depends on the shape of the object and where it's rotating about. So we had to be specific. Now we have 3 different cylinders. We have the left side, the middle part, and the right side. And so an obvious question to ask is, how do I find the combined moments of inertia when I have these 3 things? And the answer is to remember the overriding equation for moment of inertia was I is equal to the sum over all pieces of mass I times radius I squared. Remember that equation? No. We first talked about it when Andy was sitting and spinning, and then we reviewed it again when we had the lecture in lab on Tuesday. So the moment of inertia just comes from adding up all of the pieces of mass times their distance from the rotational axis squared. So if I have one thing and I know adding all of its pieces up gives me 1/2 the mass of that object times the radius of that object squared, and then I go to another one, if I add all those up, it's going to give me this equation. Since I'm just adding everything together, all I have to do is just add the 3 cylinder moments of inertia, and now I've accounted for all of the mass. So my total moment of inertia is just going to be the moment of inertia for each of the 3 pieces. So I total is I1 plus I2 plus I3, where this is piece 1, piece 2, piece 3. So note that it tells us the moment of inertia equation right there. Didn't actually need to look it up because it was given in the problem. But I have those 3 pieces, and it gives me capital M is the mass of one of these pieces. And the middle one has a mass of 1/2 of that and a radius of 1/2 of capital R, where capital R is given. So for the first one, it's going to be 1/2 capital M capital R squared. For the middle one, 1/2, and its mass was 1/2 capital M, and its radius was 1/2 capital R squared. And then the last one, 1/2, its mass was capital M, its radius was capital R. So I'm accounting for each of the 3 cylinders. And keep in mind, the reason I have parentheses 1/2 M and parentheses 1/2 R for the middle one is because it has a smaller radius and a smaller mass. So we are not unsophisticated here. 1/2 squared, what's 1/2 squared? 1/4. Times 1/2. Times 1/2. So this is 1/16 times MR squared. 1/2 plus 1/2. What's 1/2 plus 1/2? 1. 1 plus 1/16. 17/16. That's a 16 out of 10. And that's actually the first part. Part A is just calculating that. This way. Now, before I move on, I'm going to do something else because when I did this with a student who shall be unnamed, we got wrong answers. And I was really mad, like, they've got this wrong. And it's because we forgot that the mass of our yo-yo is not capital M. What's the mass of our yo-yo?
M plus half M.
That's right.
Wait, what?
The mass of our yo-yo is mass 1 plus mass 2 plus mass 3, which, as Max told us, is capital M plus 1/2 capital M plus capital M. So that's 2/2 capital M is the mass of my entire yo-yo.
Is radius the same then? Or so the MR radius is a
Well, capital R is something that's given to you. So everyone has a different capital R. In my case, it's 3.4.
It's the same, even though it's 1/2 from the other.
Well, it's 1/2 of, in my case, 3.4. Yeah, so the capital R stands for the same thing every time I use it. That's why I'm using capitals versus lower cases, is to try to differentiate between them.
I got it.
Oh, no.
Wait. I did what you said though. It's wrong. that equation right there, 17/6.
Team
Mass.
times your mass, which
Radius squared.
times that mass and that radius squared. Yeah.
That mass meaning all the masses, right?
No, meaning that mass. Capital M is that mass.
You just said.
I said the mass of our entire yo-yo is 2.5 M. But this equation is 17/16 mr squared. So that's why, let me put a subscript mass total there so that there's not the option of that confusion. David.
Should we get a small scientific notation number?
A what?
A small scientific notation number.
If I remember right, yeah, it's something in the ballpark of 10 to the minus 4 or 10 to the minus 5.
Okay.
Apparently that was a funny answer.
No, that was 400.
400?
What?
Yeah.
Units?
Yeah.
What? Bozo.
Well, okay. How many kilograms is 56 grams?
Kilograms?
That's the standard unit, isn't it?
You're crazy. Okay.
And it actually is very specific in kilograms times meters squared.
It does say that. Okay, hold up.
I
Kilograms.
have to negative force 2 grams, and it was
Shut up. It's on.
Well, let's continue with the problem because at this point we're punching numbers in calculators. I am 100% certain that that is correct. That is the 17/16 mr squared. So part B, in both cases shown, was the magnitude of torque exerted by the string about the contact point of the yo-yo with the table. Now, when we looked at this, we actually calculated about center mass, but it turns out to be the same, so we were right. So it's asking for the moment or the torque created about this point. Okay, I'm trying to find a color that's going to contrast. That would be a horrible choice. Okay, you can kind of see that point. Did I try green? Okay. I tried every color, so one of them had to be good. So, how do you calculate a torque? Yeah. Torque is equal to R cross F. Or the magnitude of the torque, because it says to find the magnitude of the torque, is equal to, it stopped writing, there we go, R perpendicular times the force. So I need to find the perpendicular distance from my green dot to where the force acts. So that's not a tough problem. We know okay, here we go. We know this here is capital R, right? And we know this here, what's the size? Actually, I want to put that up. What's the size of the orange line? half r. So what does that leave this distance here to be? That's also another half r. Why is that the perpendicular distance? Because that is perpendicular to the force going from the point where I'm summing the torque to where the force acts. It's got to be perpendicular to the line. Even if that force, well, we'll look at the other one. So it says for both cases, so we look here. Again, summing the torque about that point, and you said green was better. And so now what's my perpendicular distance? I take this line of force and I just extend it. And what is the shortest distance, the one that's perpendicular, and it's this distance right here. So that's my perpendicular distance. But as luck would have it, what is that distance of the line I drew? That's r over 2. That was one of the givens. So in both case 1 and case 2, the distance that's perpendicular to the force from the point of contact between the table and the yo-yo and that force pull is r over 2. So now that we've established what the r perpendicular is, substitute that r over 2 times the force, and I'm going to put force pull just so it's a specific force, and you calculate it. Get a number. Once again, you're not putting centimeters for your radius. What units are you using?
Meters.
Meters, yes. All right, so that's part B. Part C. What is the moment of the you got a question, Claudia?
Just going back to the original equation, sorry, to part A.
Uh-huh.
When we have to distribute the 1/2, so in the middle, when we have to distribute the 1/2 to the 1/2 in the n, in the parentheses. Because 1/2 n is in parentheses with 1/2 on the outside. So when that 1/2 have to go with the 1/2 in
We did. That's how we got 1/16. We had 1/2 times 1/2 times 1/2 squared.
But then the n should have
The first 1/2 is the 1/2 out in front.
right.
The second 1/2 was the 1/2 multiplied by n. And then the 1/2 squared was the 1/2 multiplied by r.
Right, but the 1/2 is outside the parentheses on the 1/2 n. So shouldn't it be applied to the 1/2 and the n?
It was. We had 1/2, the one outside the parentheses, times the 1/2 inside the parentheses. So it was applied.
But then shouldn't it be applied to the n? Not just like the 1/2 n.
I know this is going to sound silly, but in multiplication, you only multiply once. If I have 5 times 10 times 10, I don't have 50 times 50. I have 50 times 10, if you will.
Well, just because none of it's not.
Yeah, none of our answers are working.
For which one?
When we did it yesterday, it worked.
I'm not getting answers for anyone.
Yeah. I mean, it worked out for both of us yesterday with that equation. You're using r is.
These added up on.
No, you use r.
What you have.
You use r that you're given right here, and of course, converting it to meters. And you use m, converting it to kilograms. And yeah, I am quite certain that that is correct. So if you have problems after class, we can come talk about it and make sure you calculate it right. Because I don't want you to answer the wrong answer 7 times and get 0. Okay, so part C is the part that I sent the email about, where we have to use the parallel axis theorem. The theorem that says that the moment of inertia about a point that's other than the center of mass is equal to the moment of inertia about the center of mass plus the total mass times the distance from the center of mass squared. So notice I put m sub t, where m sub t I defined above is 2.5 m. Yes?
When I did mine, the center transfer mass, I only use the mass M given,
Right.
not the additive masses.
Correct. Yes.
It would.
So you didn't use that?
This is capital M here.
Right, which is why I think people are using their additive mass.
Are you using the total mass instead of the capital M?
Which,
Yeah.
Are we not supposed, what is this M plus half M plus M equals 2.5? What is
That's the total mass of the yo-yo. But capital M here, right? That's why I was trying to use uppercase versus lowercase to distinguish. Capital M and capital R are values given. And so I'm not going to change the name of what they gave you.
So then this capital M that's over here in red, that's
Yeah.
the M that's given.
That's the M that's given, right? So for part C, you just have that parallel axis theorem. So that's going to be your 16 or 17 16ths, not 16 17ths. 17 16ths capital M capital R squared plus my mass total, which was 2.5 capital M times the distance away from the center mass. If we go from the center to the edge, we've got a distance of R. So that distance is R squared. Yes?
Sorry, 2.5 M is the total mass.
That's the total mass, yeah.
In kilograms.
Right.
2.5 M is 2.5 multiplied by the M, not 2.5 multiplied by the total mass.
Oh,
Well, right. M sub T
okay, that makes sense. Yeah, same thing.
is 2.5
Got it.
capital M.
There we go.
And then finally, and this is going to be different than what we did. Different than what we did because they've set you up to doing it this way. Okay, it was Sarah that I worked it out with. And we worked it out. When we got to the last part, we started over. And we calculated following exactly the steps that I gave you in lab on Tuesday. And we did it for both cases just to verify that it gives you the same answer for both cases. But this problem is trying to lead you to now simply apply the rotational equivalent of Newton's second law about the point of contact. So if I'm going to apply the rotational equivalent of Newton's second law, what do I need to do? I mean, what were the first steps in solving a dynamics problem? A what? Okay, the first one was to identify this rotational dynamics problem. Yes. Yes, how would you determine it's a rotational dynamics problem to begin with? It has to have blank and blank. Rotation, because it's rotational dynamics, and it needs to have acceleration. Otherwise, it would be rotational static. Or not static, equilibrium. It'd be rotational equilibrium if it had no acceleration. With acceleration, either angular or linear, then it's going to be rotational dynamics. Then, what do? You can just read from my handout on Tuesday. No one has that handy?
What are we asking for?
After we've identified that it's a rotational dynamics problem, what do? According to the handout I gave you on Tuesday.
Draw a diagram.
Draw a diagram. So we've got pictures here, but what do I need to add to that diagram? Forces. I need to show the forces where they're acting. So here's a bigger picture of the yo-yo. And I can choose either case. Why can I choose either case? Because it turned out that the torque magnitude was the same in both cases. What forces are acting on this yo-yo? Okay, somebody said gravity. There's a force of gravity pointing down. What else?
Force normal.
Force normal, which points? Up. What else?
There's tension.
It's a tension, so I'm going to just choose to make the tension like that. I put force pulls, what I called it. And there's one more.
Rotational.
Okay, I'm going with Oksana.
Friction.
Force of friction. So now I have all the forces. What's the next step?
Apply The sum of the torques about the axis of rotation.
So sum of the torques equals 0. Now, as the problem was leading us, they intended us to sum the torques about this point. So I'm going to call it A just so I have a name for it. And so I'm summing the torques about point A.
Why is it 0?
Hey, it's not 0, is it? It's I alpha. After all, we're trying to find the acceleration. Thank you. So I need to sum the torques about point A. So what's the equation for the torque? Well, we already wrote it down here. The torque is R cross F, or R perpendicular times the force, and then we use the right-hand rule to get the direction or sign. So we have 4 forces, and once again, I'm going to write down even the ridiculous torques, the ones that are 0. So choose a force, and I'm just going to start at the back of the room. So Isabel, choose a force. Okay, so I'm going to do the torque due to FG. So what's the perpendicular distance from point A to FG? Isabel.
R.
Not R. If I make my vector from A to FG, it should be perfectly straight up. How much of that vector R is perpendicular to FG?
Is it R squared?
No, R is that vector. It's not a square. How much of a vertical line is perpendicular to vertical force if they're on top of each other?
0.
0. And so the R perpendicular is 0. And so that's 0 for the R perpendicular times FG. Okay, Oksana, choose another force.
No, friction.
Okay, so force friction. What is the perpendicular radius from point A to where the force of friction line is?
Force normal.
Force normal, not a distance. What is the perpendicular distance from point A to the line for force of friction? 0. So I'm going to have 0 again for the perpendicular distance. All right, Jenna, choose a third force. Force normal. And Jenna, what is the perpendicular distance from point A to where the force normal acts? 0. And finally, Judith, there's only one force remaining. Which one is that? Okay, so we have the force pull. And what's the perpendicular distance from point A to force pull? It's not R. What is it, Jenna? The perpendicular distance from point A to force pull. Radius squared isn't a distance. Radius is the distance from here to here. We're looking for the distance from here to here that's perpendicular to force pull. So it's half the radius. What did you say? And now we have the joy. Is it a positive or negative torque? All the rest were 0 torque, so I didn't ask you is it positive or negative. Is that a positive or negative torque? The way I've drawn it. To your solution, by the way, it doesn't matter because you're asked for magnitude. Okay, so we have a positive. It's actually negative. So we need to make sure we understand how to get these signs. So there's 2 methods. Sarah, what's your method? Sarah looks and she says, would that force make it rotate in a clockwise or counterclockwise direction about point A? And I would go with clockwise because here's point F. It's above it and pulling to the right, so it's going to make it go like that. Or point F, point A.
Yeah. Oh.
And so that's the way that Oksana and Sarah have been doing. It's going to make it go clockwise, and clockwise is negative. Randy, what were you saying?
After set this is like, go like this, essentially. And when I have your thumb, you curl around, and if it's going inwards.
Okay, well that's the same rule then. Okay, The other one is using your right hand. Well, that was using your right hand. You take your index finger, point it parallel to R, so R is going up that black arrow. Keep your index finger pointing up and orient your hand so your middle finger can point in the direction of the force pull. Thumb points in, and just like as Randy was saying, if your thumb points in, that's negative. If your thumb points out, it's positive. So that was a negative. So now I have sum of my torques equals I alpha. Why did we have part C in this? We had part C because it gave us the I. Why did we have part B? We had part B because it gave us this. And so alpha is equal to minus 1/2 R F pole over I. And that's alpha. They didn't ask us for alpha, did they?
No.
What did they ask for?
Linear acceleration.
The linear acceleration. What is alpha? Not centripetal. It's the angular acceleration. And so the question is, how does the angular acceleration relate to the linear acceleration? And for that, we have the relationship that alpha is equal to A tangential over the radius. Now, we always have to look at our signs carefully. Let's say this thing accelerates to the right, or just rolls to the right. If it rolls to the right, we consider that a positive acceleration. If it's rolling to the right, what direction do you get for the angular velocity? Is it clockwise or counterclockwise? Clockwise, so negative, right. Or you can take your right hand rule, wrap your fingers the way it's rotating, your thumb points in, so negative. So a positive acceleration corresponds with a negative angular acceleration for our definition of directions here. And so I got a minus sign here. Therefore, A tangential is equal to minus alpha R equals minus parenthesis minus 1/2 RF pole over I times R equals R squared F pole over 2I. And keep in mind, even if you had had a negative value, it asked for the magnitude. And unfortunately, I took my yo-yo into my office to illustrate this to Sarah yesterday, to illustrate the coolness with the yo-yo. If I had done the case where I pulled it straight up, I would have had the opposite sign. It would have accelerated the opposite direction. And so if you pull the yo-yo string straight up, it will go that direction. You pull it this way, it'll go that direction. Very cool. But it's in my office, and I don't want to break class, especially since I've used 60% of the class to do this problem. But it's a really good example of exactly what we did in class on Tuesday, or in lab on Tuesday. Given that we've used more than half the class period, I'm going to get right into the lecture. So on Wednesday, we started with fluids, and we talked about the states of matter and what a fluid is. Fundamentally, what makes something a fluid? If it flows. That's right. That's the full definition. If it flows. And so liquids flow, so they're fluids. Gases flow, so they're fluids. So what we're saying in this chapter includes both liquids and gases. Now, this here's a picture, two cartoons, about Archimedes' principle, which we're not going to get to today because of all the time we spent doing that problem. So let's get into what we can do. We're going to study density, pressure, and Pascal's principle. So, density. Density is a measurement of how much mass you pack into a specific volume. So, for instance, in this classroom is mostly filled with air. If I were to take a cube of air and measure the mass, do you think it'd be a large number or a small number? take a cube of air and measure its mass. Would it be a large number or a small number? It would be a small number. If I took a cube of water that was equal, would I have the same mass? More mass, less mass? More. So that means water has more mass per unit volume than air does, by a factor of about 800. And so the water is more dense than air. So density is just calculated by taking a given volume and measuring the mass. The symbol for density, M over V.
What's that symbol called?
That's rho. It's R in Greek. So density is mass over volume. This was the key to Archimedes' principle, which, like I said, I don't think we're going to get to today. So you probably have seen these silly questions to try to trick people. What weighs more, a ton of bricks or a ton of hay? Okay, so we have the silly answer. They weigh the same because they both have the same weight, the same G, hence the same mass or same force, or same mass. Yeah. So it doesn't matter for the weight if it's a ton of bricks or a ton of hay, but you clearly have to have a lot more hay to get a ton of hay than you have to have in brick, because the brick is more dense, has more mass per unit volume. And of course, this says feathers, but that has hay, and that's why I said hay. Now, pressure. We talked about stress before. What can you tell me about stress? This class gives you stress. That's accurate. And while I want you to love the class like I do, it's still going to give you stress just like anything else that you have to do. Right? The only thing that doesn't give me stress is eating, but then other people give me external stress. What is stress in a physics sense? It's the amount of force divided by area. Pressure is also the force divided by area. And so then that makes the head explode. Puts you under more stress. They're the same thing? No, they're not the same thing. They're just both force divided by area. So when I talked about stress, I talked about 3 types of stress. There was compressive stress if the force is into the surface. There was tensile stress if the force is out of the surface. So if I glued my hands to the table and pulled up, that would be tensile stress, it'd be in tension. And then there's shear stress. If I glue my hands to the table and I try to go sideways, then the force is in the plane of the surface, not into it or out of it. Just like moment of inertia is a tensor, moment of inertia you have 6 elements. Stress is also a tensor. You have the different types of stress there. Pressure is scalar. So now remember, scalars versus vectors, which one did you find easier? Scalars. Pressure is scalar. Tensors are just a step more complicated than vectors. So pressure is easier to deal with because it doesn't have directionality where stress did. Oksana has a question.
So what is a tensor?
A tensor is a multidimensional vector, essentially.
Oh, yeah.
A vector is like a rank 1 tensor or something like that. So a vector is an example of a tensor. It's the simplest tensor you can make. Well, I suppose a scalar would be the simplest. That'd be a rank 0 tensor. So pressure is force over area. What's different about pressure? Why is it a scalar? In a fluid, directionality is not a big deal. The pressure is the same in all directions. Now, you know that we have air pressure acting on us here, right? Yeah, something like that. What direction is the force that air pressure puts on your skin? Everywhere. What direction, though? That's not direction. Normal. It's always going just into the skin. So air pressure is pushing down the top of my head, it's pushing in on my 6-pack abs right here. It's pushing up on the bottom of my feet. So air pressure is pushing me in everywhere, which leads to people saying, okay, so if I was in a vacuum, what would happen to me? What do you think would happen? Okay, you would plump up. You would plump up because you're used to having air pushing in on your skin. You take that away, your skin's going to stretch out because you don't have the air pushing in. And so you are going to get bloated. And then people talk about, what about your eyes? Your eyes going to pop? Are they going to come out? By accidents in experiments, we know your eyes aren't going to pop out. But it would be a very bad thing. This picture here is just illustrating that the same force on a smaller area is a much higher pressure. So the amount of force, you push your finger on something, it makes a fairly small pressure. If you take a needle and push with the same amount, it could make a big pressure. And so it could puncture something. Units of pressure and what gauge pressure is. Since pressure is force over area, the SI unit is a Newton divided by a meter squared. Area is length times distance, so meters squared. So Newton per meter squared, we call a Pascal. That's the unit for pressure. That's the standard unit. But then I have some other ones here. The imperial unit. Imperial, that's stuff like feet, miles, and crazy things that don't make sense to most scientists. The imperial unit for pressure is pounds per square inch, or PSI for short. So when you go to the gas station and you put air in your tire, you measure the pressure in the tire in PSI, in pounds per square inch. And sometimes people will say pounds, and of course that's not right, because what would pounds be? Unit of force instead of pressure. An atmosphere. Now, let's be clear. Atmospheric pressure does change. Sometimes it's higher, sometimes it's lower. But the standard, which is an average for if you're at sea level, is 1 atmosphere is 1.01325 times 10 to the 5th pascals, or 14.70 pounds per square inch. So that's another unit that we can use. So we're going to have to, at times, convert from one unit to another. And then the last one I have here is torr. How many people have ever used the pressure unit torr? Okay, we have a good number. Where did you use it, Andy? In chemistry. And what was the definition of a torr? It's a simple definition. It's even known by that definition. Go ahead. Has something to do with mercury. It's also known as a millimeter of mercury. And as we go through on this topic, we'll see where that comes from.
It's similar to bar, maybe?
Actually, a bar is 10,000 pascals. So it's similar to an atmosphere. It's basically, well, let's make a metric value. So, 1 atmosphere is 1.01325 bars. At least that's my recollection. I didn't even put it on the list. So,
No, that sounds good.
Gauge pressure. We actually are more familiar with gauge pressure than we are with pressure, because we're usually mostly familiar with pressure when we talk about putting air in a tire. Hence, I've already referred to that. But when you put air in a tire, you put in, let's say, 32 PSI gauge, not just 32 PSI. So what's the difference? Well, it's written up there. Gauge pressure is the difference between a reference or a gauge and the absolute pressure. So the absolute pressure is how many pounds per square inch is it pushing? Gauge pressure is going to be, well, let's take that and subtract a reference. And that reference is almost always atmospheric pressure. So if you have just a little air pressure gauge, that air pressure gauge has a cylinder, and in the cylinder there's a stopper that can slide easily. And on one side you have a spring. Baby, come back. No. Watch, I'll draw another spring and then it'll appear. Okay, so you have a spring. Normally, if it's open, you have air pressure on both sides of that stopper, and you measure that as 0 PSI gauge pressure. So whatever its position is when it's just open to atmosphere on both sides is, and actually I probably should have left myself an air gap here so it doesn't look like it's blocked because air can flow in and out. But then when I put high pressure here, so I connect it to my tire, and have pressure tire here. If the pressure in the tire is higher, then it's going to apply a force to that surface. If pressure is force over area, how do I calculate the force it's going to apply? Okay, pressure is force over area, so what is force equal to? Area times pressure. So I'm going to have a force of area times pressure pushing on the left side. Left side? Yeah. On the right side, I still have a force. So this is area times pressure in the tire on this side. And on the other side, I have area times pressure atmosphere. So I have those two forces. If the pressure in the tire is bigger than the atmospheric pressure, I have a net force pushing which direction? To the right. And so it pushes to the right and it's going to compress the spring. But what does the spring do when you compress it? It pushes back with a force of K delta X. So I have from the spring an additional force here of K delta X. And so it will reach equilibrium when I have some of the forces equal 0 at equilibrium. So I'll have A pressure tire, well, let's be minus A pressure atmosphere minus K delta X equals 0. And so if you saw that for delta X, you get delta X equals A times pressure tire minus pressure atmosphere all over K. And what do we call pressure tire minus pressure atmosphere? The gauge pressure. So the amount that thing moved tells me the gauge pressure, which conveniently enough we measure with a pressure gauge. Yeah, look at that. So gauge pressure is an important thing to understand. So here's a picture of a tire. You have air in there. What's the point of having air in your tire? To move. To get the car off the ground. We're going to do a problem here. An automobile weighs 3,461 pounds. That's the maximum curb weight for Nissan Altima. Huh?
Gallons. 10 gallons?
No, that's the weight of the car. So the weight of the car is 3,461 pounds. Assuming that each tire supports 1/4 of the car's weight and is inflated to 32 PSI, what does a PSI mean? Pounds per square inch, gauge pressure. What area of rubber meets the road for each tire? Do you understand the problem?
Yeah.
Okay, do you understand the solution? If you did, then maybe class today was, below you. Uh-oh. So first thing I do, of course, is I draw a picture. Because, what else are you going to do? And you see that we're no longer in the dynamic section, but we're not getting rid of forces, are we? So I have a piece of rubber, and this is just the rubber that meets the road. What do I have for pressure above and below that rubber? Do I have pressure above it?
Yes.
Yes. What should we call that? Tire pressure. Now, the way the car is going to come into everything, but we have tire pressure there. And that tire pressure is then going to apply a force on the surface, right? What about below the tire? Okay. Below the tire, I'm going to have a force normal. Since I'm in red now, I'm going to put here force in is equal to pressure tire times area, right? Since that's the relationship between pressure and area. But what about air pressure? Do I have air pressure outside the tire? Yes. What's that value?
What is FN?
Fn is the force on the inside of the tire pushing on the rubber.
Can we call out the force tire?
No.
Okay.
No, because then we'd have two forced tires and they'd mean different things. 1 atmosphere, that's right. We have 1 atmosphere on the outside. And what direction is the force that the atmospheric pressure is going to put on this piece of rubber? Normal to the surface going in. Always going in. There's no such thing as a negative pressure. A negative pressure would mean a force pulling out. You can only do that if you glue your hand on, right? If you were to glue the fluid to your material, well, you can't do that. So you would have that for air pressure, and that's pressure atmosphere. And so going to my forces, I'm also going to have an upward force of force out equals pressure atmosphere times area. So now if I look at this piece of rubber, if the car is, let's say, parked. Let's just keep life easy. If this car is parked, is this a dynamics or an equilibrium problem? Equilibrium. So if it's an equilibrium, then my conditions are things like sum of the forces equals 0. So the sum of the forces, and obviously I'm going to sum this in the vertical direction. Why? Because they're all vertical forces. Is equal to 0 because equilibrium. So if I look at my picture, I have force normal plus force out minus force in equals 0. And then if I put in my equations for force out and in, now I'm getting somewhere. What am I trying to solve for? So I'm going to move the two terms with area to the other side, the equal side, and factor out the A. So I have the force normal is equal to A times pressure tire minus pressure atmosphere.
And divide by the pressures.
Divide by the pressure difference. So we have an equation. The area in contact is equal to the force normal for that tire divided by pressure tire minus pressure atmosphere. The pressure tire minus pressure atmosphere, what do we call that kind of measurement? Yeah. And so now I can put in numbers. The force normal, I said that assuming that each tire holds up 1/4 of the weight. So the force normal is going to be 1/4 of the entire weight. So I'm going to have 1/4 of that 3,461 pounds. Divided by my gauge pressure, which was 32 PSI. I'm now going to write PSI as pounds per square inch so I don't get my units confused. You had a question?
Do I have to multiply that by 921?
No, because we don't have any masses involved here. a pound is a force. So 3,461 divided by 4, and then divide the whole thing by 32. What do you get? Yeah, we all race. So we get 27 square inches. So 27 square inches, you can take the width of your tire and then calculate how long you'd have to have contact to get 27 square inches. So when you have a tire that's flat, it has lower pressure inside. It's going to have a bigger area in contact to support the car. And so that's why it crumples down, because to get more area of contact.
Is that why we have softer tires in the wintertime?
Well, naturally, as it gets colder, your air contracts, and so the pressure inside is going to drop. And so you need to inflate to get more air to get back up to your regular pressure. But then when you start driving, the air inside gets warm, and it will reinflate. And so you want to measure the warm temperature air pressure when you fill up with air.
Tire beating, tire pressure is low.
Yeah. So like it probably will be when you first start out driving. And if you drive for, half hour and it's still low, you got to put some air in. Okay. Have a good day, a good weekend, a happy Sabbath. And you have a question.
What did you see?